A worm-like synthetic material can learn, forget, and relearn new shapes without a central processor, mimicking living systems.
Researchers at the University of Amsterdam's Machine Materials Lab have created a new class of metamaterials that don't just bend or fold, they learn. Published in Nature Physics, the work introduces worm-like chains of motorized hinges that progressively learn to change shape by example, then remember, forget, or toggle between multiple shapes on command. Unlike conventional materials with fixed responses or robots running pre-programmed code, these systems adapt without a central brain, mimicking the way cells and brainless organisms adjust to changing conditions. The material is built from identical motorized hinges linked by an elastic skeleton. Each hinge contains a microcontroller that senses its rotation, stores past movements, and exchanges data with its neighbors. Using that information, the hinge can apply a torque that tweaks its own stiffness and preferred position. Over repeated training examples, the chain as a whole learns a target deformation, say, curling into the letters that spell learn or, in Dutch, leren. Once learned, the shape can be recalled, overwritten with a new one, or the material can switch between several memorized configurations. That ability unlocks surprisingly lifelike behavior. The chains can perform reflex actions, grab objects, or generate locomotion by cycling through learned shapes. The most exciting observation was that learning gives our metamaterials the ability to evolve. Once the system starts to learn, the possibilities of where it ends up feel almost limitless, said Yao Du, PhD candidate at UVA and first author of the paper. Because the learning happens locally at each hinge through neighbor-to-neighbor communication, there's no centralized controller to reprogram. The material itself embodies the computation. The Amsterdam team, led by Corentin Calais, sees the advance as a step toward materials that blur into machines. Earlier work from the lab showed brainless locomotion in odd-shaped metamaterials using intricate mechanics, but those designs lacked memory or learning. The new system adds both, turning passive structures into active agents that rewrite their behavioral code. Future work aims at time-dependent behaviors, teaching the chains different gaits like crawling, rolling, or wriggling based on environmental cues, and at learning under noise and uncertainty, so the materials stay robust in unpredictable settings. This fits the Dutch Research Agenda's 2026 theme, materials that learn and learning how we responsibly use them. A new PhD position, co-hosted with the Malf's Learning Machines group, will push the concept toward dynamic, multifunctional devices for robotics, adaptive structures, and biomedical tools. As the authors note in their AR14 preprint, the findings establish metamaterials as a platform for physical learning, opening avenues for adaptive materials and robots that don't need software updates to gain new skills. They learn by doing.